Start recording. All right, so welcome to yet another session, the second chapter, and we're going to be looking at the introduction to compute virtualization. So you could be there and asking yourself, why we've been bothering ourselves to, look at compute virtualization. What is virtualization anyway? We said in this chapter that cloud computing version 1.0 focuses on virtualization. And we said previously that virtualization helps us to separate applications from the underlying operating systems and hardware in the traditional IT systems. Whereas cloud computing relies on that split. For us to be able to get cloud computing means that we have to find a mechanism of separating our applications from the underlying, software, hardware resources. So cloud computing relies on that split. So virtualization and cloud computing can both be used to build highly available and reliable runtime environments for our application, though they also differ in quite a number of ways. The most apparent difference between the two is that virtualization provides only the infrastructure as a service. Remember, we looked at what infrastructure as a service is. We looked at, we said we can deploy the cloud. We can categorize it either by deployment model, the way it is deployed on the cloud, or we can also characterize it either by service model, depending on what they're going to use the cloud. By service model, remember we said we can get services either as infrastructure as a service. We also looked at platform as a service, and also we looked at software. Please mute your microphone, Obere Gova. You don't mute your microphone, I'll put you in the waiting room. And software as a service. Okay, so these are the three service levels that we looked at. With infrastructure as a service, who remembers? We talked about it, and we said here that a cloud service provider looks at everything at what kind of level, at what layer? Yes, Hope, your hand is up.
So your screen is not displaying. I don't know whether it's me or it's my problem or it's...
My screen is not displaying.
Yeah, I'm just seeing the introduction, just the introduction to come.
That's where we are.
That's where we are.
I'm seeing it.
Aren't you seeing me writing on the screen?
That's where we are.
That's where we all are on the screen.
And
introduction to computer.
Yeah, but we can see you writing. We can see you writing. I can see you. I don't know.
Okay. All right. I think Hope, either cross-check with your network, but we are on introduction to cloud computing, but I'm also writing on the screen, so you should be able to know that it is real.
Yeah, I now get you.
All right. So we said here that everything...
Yeah, I now get you.
Okay. The operations and maintenance here at this level are all being catered for by the cloud service provider or the infrastructure. They just give us like a computer in the cloud, like a server in the cloud. So here, what you do, you install your operating system, you go ahead and install, the middleware, you go ahead and install the runtime environment by yourself. With platform as a service, they have gone ahead and also installed an operating system for you. They have gone ahead and installed middleware, drivers and applications for you. They've also gone ahead and installed runtime environments for you. All you need to do is just access the platform, put there your data, and install there your applications, and then you're good to go. And this is commonly used by developers. With software as a platform, everything else, even the application data and also the applications are pre-installed. All you need to do is access the services, maybe punch in your credentials, and then you use it. So we are saying here that with virtualization, the difference is that virtualization only provides us with infrastructure as a service model, while cloud computing can provide us other service models like the platform as a service or even software as a service. So virtualization is the foundation of cloud computing. And now I think that answers our question, why should we even look at compute virtualization? So that's why it is important for us to learn about this technology before even delving into cloud computing technology, because we need to know now, you're telling us we can access all those resources in the cloud. True, yes. But now, how do they even put all those resources together? What technologies do they use to virtualize the different, let's say CPU, memory, or even storage, so that we can access those resources from the cloud? That's why we are saying that virtualization is a foundation of cloud computing. Virtualization allows the operating systems and applications to run on virtual machines, okay? And you may be asking yourself now, what is virtual machines? Don't worry, in this chapter, we shall describe briefly how we can be able to create virtual machines and even how virtual machines work. So moving forward, we said already that cloud computing 1.0 focused on virtualization, which today has become the foundation of cloud computing. This chapter focuses on the architecture and technologies involved in compute virtualization. Upon completion of this course, you'll be able to describe what virtualization is. You'll be able to understand the differences between virtualization and cloud computing, and also understand the KVM technology and understand Huawei Fusion Sphere virtualization technology. So let us look at the introduction to virtualization, and we ask ourselves, what is virtualization? Some of you have heard of what virtual machines are. What is a virtual machine? We have two things here to pay attention to. We have virtual and we have a machine. So if we combine them together, in your own opinion, can someone just tell me, mic check, and they tell me what they think of what a virtual machine is?
Mic check.
Go ahead.
So I feel like a virtual machine is basically when you virtualize the hardware, sort of like the RAM and the storage, is a way you can virtualize it, and the OS believes that virtual hardware.
Okay. All right. Thank you. Anyone else?
Yeah.
Okay. It's just an emulation of a physical machine.
Very good. It is just an emulation of a
physical machine.
Of a physical machine. Very true. Right. I just want to, just a moment. Just a moment. Just a moment, 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 just a moment. Okay. So it is an emulation of a physical machine. We said that virtualization is a technology that stimulates hardware functionalities and creates multiple virtual machines on a physical computer. You will all agree with me that under traditional infrastructure, if you have your server or a computer, you cannot install and run more than one operating system on the same hardware resources directly and run them concurrently. Can you do that? Either you have to dual boot, or you have to create some kind of virtualized environment for you to be able to install and run at least more than one operating system. Isaac, your hand is up.
No, I was gonna say it was not possible.
Yes, it is actually not possible.
When you have just one machine.
Yes. So if you want to have more than one operating system at the same time, that means that, you know what, either you're going to use dual boot, and whenever you're accessing your machine, you boot out of Windows, then you power it off, And then after you log in as let's say Ubuntu or Linux, or depending on whatever you wanted to, whatever operating system you installed on your machine. And that is a hassle. Now imagine if it's a server and there are applications that other people are relying on. And whenever you want to access another operating system, you have to, first power it on and then dual boot and then create another partition for that operating system where you'll be able to access the files. So that's why virtualization plays quite an important role, because it gives us the ability to reuse the resources, and it gives us the ability to fully maximize resource utilization. That we can use the same hardware resources and we can go ahead and have as many virtual machines as possible. I have my, I can either use Oracle or I can use VMware Station. On the screen here, you're seeing my VMware player workstation. And if I wanted to create a machine, I don't even have to stop this class and shut down and create partitions and install the operating system. I can just go ahead and say create a partition, select where I'm going to get the operating system, and say I want to create an Ubuntu operating system. Go ahead and create next, give it a full name that I want. I say we'll be using Sandy Samuel, will be the name for the machine. The username will be Sandy, and then my password will be what will my password be? Okay, will be that password. So I go ahead and press next. It will ask me where I want to store and keep my virtual machine. I'll select the destination. I say in this particular case, I don't want it on my C drive, because my C drive is synchronizing and backing up in the cloud, and I don't want it to waste my space. So let me just navigate and take it on my other drive. And on my other drive, I have a folder for VM and also a folder for my virtual machines, VMware. So I go ahead and select, I want to give it what capacity. Maybe I should give it 20, it should be okay, and I should split it. Go ahead and customize hardware. On your hardware resources, you choose whether I want to give it 4 GB of my memory. I can give it up to the number of, memory I have in my, I have on my machine, and I can also go and enable virtualization for it. I can go ahead and select the different drives that I want it to use, the network adapters, either add one or even do whatever I want. You can add as many network adapters as possible. Go ahead, go to sound cards and memory, and then give it the resources I need. And after, when I'm done, I go ahead and click on finish, and boom, I have created a virtual machine, and my virtual machine, ladies and gentlemen, is booting up, and I'm going to install my operating system on it. And after installing my operating system on it, as you can see, it has already started. It is booting up, and I will download the updates later, and it's checking on the disk. As you can see already, ladies and gentlemen, it is booting and creating my Ubuntu virtual machine. So I have not switched off my computer. I have not powered it off, and I will just minimize it and continue with the class. I'll come back later. I'll come back to it later on when it is done, and then we'll be in position to talk about more details. So that is what we are calling a virtual machine. So a virtual machine can be installed on a computer, and we can use that to share as many resources as possible. So this is a virtual machine. Okay. And how is a virtual machine created? You just have to have a hypervisor, or what we call a virtual machine monitor or manager. And then we go ahead and, select those different resources that I've selected. I can either create the one for Ubuntu, I can go ahead and, give it the different resources that it needs to be able to access. So this is what we are calling virtualization. So generally, application needs to run inside on an operating system. And like I said, only one operating system can run on a physical server at a time. That's why virtualization allows virtual machines that reside on the same physical server to run independent operating system. And later on, we shall come to appreciate that this way we can run multiple operating systems concurrently to run on the same physical server, sharing the same physical resources. So the essence of virtualization is to separate software from hardware. How does it do that? It does that by converting our physical resources, the hard disk, the memory, the CPU, by converting the physical devices into some kind of logical resources. And ladies and gentlemen, I'm hearing Ubuntu already telling me things here. As you can see, it is installing. Okay. As you can see, it's installing and verifying the installation. Already my machine is powered up. If I was going to do this manually, I would have to first create a different partition, and then after go ahead, create a bootable, drive, go ahead and switch off my computer here and dual boot if I wanted it to be installed on the same machine. That means I had to, interrupt the class and stop Zoom and shut down and, boot into that different operating system for me to be able to access that operating system. So this is one of the importance of virtualization. And my virtual machine is already installing Ubuntu, and maybe when we are done, we can also go ahead and install also another, maybe Windows operating system, and then we shall be able to understand. So before virtualization, we need to locate the physical devices running our applications in the real world environment. And we need to be able to understand what are some of those physical components. Some of the physical components are like physical servers. Inside our physical servers are like CPUs, memory, hard disks, and network adapters. All right. So we are already looking at virtualization. It helps us convert our physical resources into some kind of logical folders. And after converting them into logical folders, then we divide them into our, configuration files and also our user data files. So virtualization concepts converts our physical resources into logical folders or files. And these folders or files can now be divided into two parts. Those that store the configuration files of our virtual machine, and those that store the data, the user data of our virtual machines. All right. And those are store the virtual data of our virtual machines. So this is the logical file. And then from there, having the configuration files and also having the user data files. So we can create virtual machine 1, virtual machine 2, 3, 4, 5, 6, 7, and 8. And all these are different virtual machines. But remember, they're all sharing the same physical resources of our physical server. So now before we talk about more about virtualization, it is important for us to understand some of the brief background or history of virtualization. But before we talk about that, let me just say that without virtualization, running multiple primary application programs in the same operating system or physical server may cause runtime conflicts and also performance bottlenecks. Running only one application on a dedicated server could solve the problem but easily cause low resource utilization. With virtualization, you can have multiple virtual machines, and at the same time, you can also, each virtual machine can run an independent operating system. This one helps to improve on resource utilization, and in addition, virtualization frees application from being circled to a single physical server by allowing us to, dynamically migrate these virtual machines across a cluster. So in case one physical server is faulty in a cluster is a group of different physical servers. So in case one of them is faulty, our virtual machines, ladies and gentlemen, can easily be migrated onto a live server in our cluster, and this helps us to get features like high availability. Our machines are always available. We can also get dynamic resource scheduling, and also distributed power management, and we're going to look at these details later on. So it brings a range of benefits for enterprise data centers, such as portability of workloads, server consolidation, fault tolerance, and low management costs. And we shall, when we come to introduction to some of these features, we shall look at them in chapter 5. So don't worry, let us look at the brief history of virtualization, and we're going to just peruse through this. In 1964, IMB began to explore virtualization on mainframes. IMB has also played a very important role as far as virtualization is concerned, and in 1972, IBM was launched virtual machines running on mainframes, and in 1999, virtual machine VMware launched the commodity x86 based virtualization products. In 2002, Zen was officially launched. We have an entire topic covering Zen, so we shall also look at it in detail, but Zen was officially open sourced in 2002, and ChromeNet first announced KVM. We shall also look at KVM because the Fusion Sphere and Fusion Compute, which are Huawei virtualization products, they are built on the KVM technology. HP also launched HPUX Integrity VMs in 2007, and in 2008, Microsoft added Hyper-V. Hyper-V is a virtualization solution for Hypervisor for Windows, and it launched it in 2008, and still in 2008, Linux Container LX was launched. And then in 2010, by default, Red Hat 6.0 supported KVM as the only virtualization option. And even today, most of the Linux tools support KVM as the virtualization product, and we shall look at it later on. So in 2011, IMBA, Red Hat, and HP and Intel formed what they called an Open Virtualization Alliance to help accelerate the adoption of KVM. And you can see how KVM has been traveling and how it is also playing an important role. So Docker was launched in 2013. We shall also get a glimpse of Docker in chapter 6 when we come to cloud computing trends. And in 2014, Rocket was also launched. So let us look at some of the important concepts of virtualization and the different types of virtualization to better understand what virtualization is. As you can see on the screen here, we say that before even talking about the types of virtualization, we need to learn some terms that are commonly used in virtualization. We have things like guest operating system, we have like guest machine, we have like hypervisor, we have like operating system, and we have a host machine, okay? And we have like a host machine. So let us look at the guest operator. Let us start here from down. The host machine. Like you hear the word host machine. He is the host. He's the one hosting things here and there. So the host machine, under normal circumstances without virtualization, we have a physical server. On our physical server, which is the host machine. Under normal circumstances, we install our host operating system. In this case now, in this example, my Windows 10 is my host operating system, which I'm using to run this class, and I've installed Zoom on it. And Zoom could also be one of the applications that I've installed on my host operating system, which is Windows 10 here, right? Which is Windows 10. But when it comes to virtualization now, and we have our virtual machine, we have our host machine, my laptop, which I'm using to teach. And now we have what they are calling an host operating system. This is the operating system, my Windows 10, which I'm using to run. It is an operating system running in a physical machine. We have what they are calling a hypervisor, or what they are calling the virtual machine monitor, the VMM. The virtual machine monitor is basically a tool that is going to help us, virtualize our underlying hardware resources of our physical machine. Some machines do not have host operating system. They have the hypervisor installed on them directly. And it is basically a machine that is designed and built to do virtualization. So instead of having a host operating system, it instead has a hypervisor. And we shall look at that type and we try to differentiate. So we have a guest machine. Like you hear the word guest machine. A guest machine is a virtual machine that is installed inside our virtual machine monitor or our hypervisor, and it is accessing our virtual resources from our physical machine. So basically, it's a virtual machine running on top of our hypervisor. And then the guest operating system, it's just clear that the guest operating system is running inside our virtual machine. The operating system, like you have seen me installing Ubuntu. Ubuntu here is my guest operating system. And Windows, this operating system I'm installing here or under inside my hypervisor. Here, VMware is my hypervisor. There are also other hypervisors like Oracle, okay? Like Oracle VirtualBox. Oracle VirtualBox, if I open it, you know, it opens in full screen mode. Okay. I can't move it to your screen. Let me see if I can change the settings very fast. Okay, this is my Oracle. Oh God, the operating system is really, the things are really very small. So I'll just ignore that and close out of it. Okay, forward to okay. Okay. I will just move forward. So as you can see here, my Ubuntu is my guest operating system and I am installing it. And here my operating system, Windows 10 is my my host operating system. I hope that makes sense, ladies and gentlemen. Okay, so I will go ahead and move to the next stage. So my host machine is having Windows 10 Pro 64-bit running inside it. So this is what we are calling our host operating system. Now let us try and look at the types of virtualization. We have two types of virtualization or two types of hypervisors. There are two types. And many people also sometimes come up with a third one, which are calling containers. But in this course, we're going to just focus on two types. There's type 1, which they also call bare metal. And there's also type 2, which they also call sometimes hosted virtualization. We're going to look at them and try to understand. So with type 1 hypervisor, which is also called bare metal, like you can see here, this type of hypervisor has direct access to the hardware resources and does not need to access the host operating system. That is a difference here, that we have our machine. When we have our physical server, instead of installing there a host operating system, we just install the hypervisor to act as the host operating system, and this hypervisor directly accesses our hardware resources and does not need to have access to the host operating system. This is what we are calling bare metal, or this is what we call type 1 hypervisor. So this hypervisor is seen as a customized host operating system, which merely functions as a virtual machine monitor or a hypervisor and does not need to run any other application. Its job is to virtualize the hardware resources, and it does exactly that. It identifies, captures, and responds to privileged CPU instructions. And we're going to look at those privileged CPU instructions in the next coming few slides. But its job is basically to look and look out for those instructions, or look at the protection instructions that are sent by the virtual machines. The privilege instructions and protection instructions will be discussed when we get to CPU virtualized section. So what happens here is that if the virtual machine needs to access physical resources, it will just tell the hypervisor, and the hypervisor is going to manage all the resources and the virtual environments. The hypervisor here will access the hardware resources like CPU, memory, and it's going to control the input and output devices. So here you can install virtual machine 1, virtual machine 2, virtual machine 3, go ahead and install guest operating system 2 and 3 and the access. But this guy is helping them to manage our RAM memory, which is here, our storage, which is also here, and our CPUs, which are there. So basically we use this is type 1, and we don't need a host operating system. So type 1 is dedicated to converting. Type 1 is dedicated to converting. Someone was saying something. I didn't get you.
Actually, I want to ask something.
Yes, please.
Any practical application? Sorry.
Can't wait to have the questions at the end so that the lecture is not, interrupted. But you can ask.
Okay. Next time I'll take care of it.
Okay. What did you want to ask?
Actually, can you please give a practical example of type 1 virtualization, or we are using in today's world or not?
Oh, we are going to be able to share them, but we have examples of type 1 like Zen, like EXI for VMware. We are going to look at them as coming to that, but there are those examples. So examples of VMware type 1 examples of type 1 bare metal hypervisor. We have VMware. VMware has a solution where you can go ahead and install directly what we are calling the ESX server. It doesn't come with an operating system. It just comes with VMware, hypervisor to virtualize the underlying hardware resources. Another example that we have here is Zen. Zen is also type 1. And a common example are some of the Zen servers, or what they call sometimes Citrix servers. Another example sometimes is Fusion Compute. Fusion Compute is a Huawei virtualization product, okay, for type 1. You install it directly on the machine. You don't need to have an operating, you don't have to have a host operating system for you to be able to run those devices. So let us look. Type 1 has the advantages because it is installed directly on the hardware resources. It can run different types of guest operating systems and applications independent of the host operating system. The disadvantage is that because now you need to, to develop the kernel that will be suitable for all the hardware, hardware requirements and resources, it is sometimes difficult to develop at that layer. So that is a disadvantage of type 1 hypervisor. So let us look at type 2, which we are calling hosted virtualization. Now type 2, which is hosted, like you hear the word hosted, you can see you already have your operating system installed. So quick question, the kind of virtualization you saw here that I'm using, which type is it? Is it type 1? Is it type 2? And give reasons.
Type
2.
Why is it type 2?
Type 2.
Because there's an OS.
There's a host. There's a host operating system.
OS.
Okay, very good. It has a host operating system, and which is installed this time. It is my Windows 10 Pro, and then I've gone ahead. I have other applications like Zoom running. Please mute your microphones after. And then I've gone ahead and installed VMware Workstation, which is my type 2 hypervisor. And I've gone ahead and created a virtual machine, and I'm now installing Ubuntu on it, right? I can even go ahead and create another virtual machine and install any other guest operating system that I want. Please mute your microphone, Onen Patrick. And then I can go ahead and install another guest operating system. The advantage is that they're very easy to implement. Just like you saw, I just clicked few clicks and then I've implemented it. But since it is running on top of an operating system, wow, someone has hijacked my screen. You have earned yourself a place in the waiting room. Hope. Okay, are we back?
Yes, we're back.
Yeah, we are back.
Yes, we are back.
Okay.
Yes, we are back.
Okay. Sorry about that. So I was saying the disadvantages, because it is running on top of another host operating system, it can be installed and used, right? But the performance overheads are hard because now my operating system is also consuming resources. The hypervisor itself is consuming resources. And also it should note that if you have, like, let's say some virtualization tools, they should be supported on that operating system for you to be able to install them. Some applications, they only run on Windows, and some applications only run on Linux or even Mac OS, depending. So some of the examples already that we can say for type 2 virtualization. Who can give me one example? You have even already seen it.
VMware.
VM, where workstation or player.
Oracle VirtualBox.
Oracle VirtualBox, very good. There's also KVM.
VM workstation.
Oracle VirtualBox.
Oracle VirtualBox, thank you. There's also KVM, and these ones run on top. KVM runs on top of Linux, and these ones can be installed on either Windows or Linux or even Mac OS, depending on the on the operating system. So both type 1 and type 2 hypervisor processes possesses the partitioning, isolation, and encapsulation and hardware independence features. And we're going to look at some of those features in the coming few slides. So what are some of the characteristics or benefits of virtualization? We have looked at partitioning, we have looked at isolated, we have looked at encapsulated, we have looked at independent. When it comes to partitioning, all right, it indicates that the virtual machine monitor or the hypervisor has the capability of allocating server resources to multiple virtual machines. It logically partitions those virtual machines, those underlying hardware resources like your memory. It's going to partition them and it will allocate them to different virtual machine. And each virtual machine can run an independent operating system. It can either be the same or even different from that of the host operating system, so that multiple applications can coexist on the server, and each operating system gains access only to its own virtual hardware resources, like the virtual network interface card, like the virtual CPU, like the virtual memory. So you have your virtual resources that are being, pulled from your physical resources. So it partitions these resources and gives them to different virtual machines. That is one feature of virtualization. One is partitioning. So resource quotas here, we have seen that they are allocated to each partition to prevent resource overuse by virtualization. And each virtual machine can even install its own guest operating system, and they can coexist and they can run independent of each other. The other characteristic is isolated, or what we are calling isolation. Here we can have multiple virtual machines created. Because of using partitioning, we can partition the underlying hardware resources and we create multiple virtual machines, and we go ahead and install guest operating systems, which guest operating system are totally logically isolated from each other. Remember, we said when we are creating virtual machines, it's going to get our hardware resources and it's going to convert them into logical files and folders. And each guest virtual machine will be given its own logically isolated resources. So the isolation features helps us to solve the problem of hardware failure. Because in case one virtual machine fails, the operating system maybe fails, or there is a virus or anything, it will not affect guest operating system 2 or 3. These guys will continue operating, and these guys will continue operating. Then maybe you just log in as an administrator and fix this and you bring it up, or even it will be migrated depending on the cause of failure to another, physical server. And then, but it has not affected the performance of other working virtual machines, which is quite important to us. So even if there is some kind of viruses, because this guy is isolated, the viruses will only propagated inside here. They will not be in position to attack or affect, the other guest operating systems, because they are isolated from each other. And this isolation feature allows us to control resources in order to perform implementation or performance isolation. Okay, so here it helps us to make sure that failure of one guest or virtual machine does not affect the other, and the virtual machines are totally independent of each other and they're isolated from one another. Another feature is encapsulated, and you can see how all these features are interconnecting and working together. We said with virtualization, it's going to convert our physical resources into logical folders. Okay, it's going to convert them into logical folders. This way, it makes us easy. Configuration files like let's say the BIOS configuration, hardware configuration, memory status, disk, CPU, everything can be, logically converted into a logical folder. And it makes it easy for us. We can copy, we can save, we can even move the virtual machines. And as long as we have the same, a hypervisor that supports that format, we can even open it from another computer, as long as easy as that. So you just transfer the files and then you are able to open it to another computer, and this is encapsulation. Encapsulation is one of the most important features of virtual machine migration and virtualization, because when it's migrating, it's going to migrate these logical files and then it will go ahead and open it on another physical server. So this is because encapsulation is encapsulating a virtual machine as a set of hardware independent files. It makes it easy for migration and also to make it easy to hot swap these virtual machines and put them on a different hypervisor. We can look at independence or hardware independence. When it comes to hardware independence, here a virtual machine is encapsulated into a group of files. We have already looked at encapsulation and we know what it means. It's going to convert those physical resources into logical files. We said it's going to divide them into configuration files and also into user data files, right? Which user data files and configuration files can just be configured, transferred, migrated, copied, or even moved, or even saved onto another computer, making backup extremely easy and also making migration extremely easy. So the virtual machine is completely independent from its underlying hardware here in hardware independence, and you can migrate the virtual machine by copying the virtual machine device file. Just go to where the configuration file is or the disk file and copy it to another host, and boom, you open the virtual machine and it runs. You don't even have to reinstall the operating system, and it runs from the state when it was last saved. So because the underlying hardware device is shielded by the hypervisor on it, the migration can be successful as long as you're using the same hypervisor or a hypervisor that supports that kind of file to open and to run it. Okay, so this is as similar as you having a PowerPoint file. Even if you're working on it from my computer, you just copy it to your computer as long as you have Microsoft PowerPoint. Okay, as long as you have Microsoft PowerPoint, you'll be able to open the file and you'll be able to work in it. Whether you migrate it and take it to another computer, as long as you have Microsoft PowerPoint, you'll be able to open your file and you'll be able to run the file. So let us look at CPU virtualization. We're going to now look at different things of virtualization. We said when it comes to compute resources, we have different resources of compute. We have the CPU, which is quite important. We have the memory. These are three things we're going to look at. And we have our input or output devices. These are the three things that come or make up our computing power. All right, so we're going to now look at CPU virtualization, okay? So when it comes to CPU virtualization, and before we talk about CPU virtualization, we need to understand some of the hierarchical protection domains of CPUs, often called protection rings. And there are four: ring 0, ring 1, domain 2, and ring 3. So these things were, the people who designed the CPU thought it was that, as the CPU is like the brain, for us to be able to control what accesses what instructions are set, not everyone who has the capacity to set or change things, we need to come up with some kind of levels or protection domains. That there are some things that run at a given level, and there are some things which also run at a given level. And the more you go down to ring 0, and ring 0 has direct access to our hardware resources, and that's why ring 0 is the most privileged. So these people are like, everything that will be running on ring 0, usually it's the operating system and things of that like, and there are things which have direct access to the hardware resources. And then some things now, they should, first, talk to either the operating system to be able to gain access to, send those commands to our, hardware resources, to access those hardware, underlying hardware resources. So generally, the operating system and the drivers have this privilege of ring 0, the most privilege, okay? And ring 3 has the least privilege, and applications usually run at that level. So to protect the computer, some dangerous instructions can only be executed by the operating system or even the drivers. So this helps us to prevent malicious software from randomly calling our hardware resources. For example, you will see most of you who have installed applications on, let's just give an example of Android, and you have installed WhatsApp on your, how do they draw the icon of WhatsApp? I hope that's how they draw it. You have installed WhatsApp on your phone. The first time you're using it and you want to access a camera and you want to take pictures, WhatsApp will tell you, hey boss, actually your operating system is not even WhatsApp. A dialog box will appear on your screen and tell you, hey boss, WhatsApp is trying to access your camera. Do you want us who have the privilege to access those hardware resources? And that is Android saying, and it is working at ring 0. And it is saying, do you want us to give WhatsApp permission to be able to access our camera for it to be able to take pictures? And then you either tell your operating system, in this case Android, either to allow or to deny. Has it ever happened to some of you? Of course, the answer is yes. If you have held Android devices, you see that a lot. So in this case, because applications like WhatsApp operate at ring 3, and they need permission from the operating system at Android, which operates at ring 0, to access the underlying resources. And this is basically done to help protect our hardware resources and protect our computer from malicious codes. Imagine if all applications were performing at this level, people would make malicious applications, and before you know it, people are seeing you in your bedroom sleeping, or when you're naked, or even when you're doing anything else. So this is the ring protection architecture, and those people decided to come up with that kind of architecture so that we are able to protect our operating system. So the operating system has common hosts. It sends usually two types of instructions. It sends what they call privileged instructions. Let me try and clear my screen. It sends what they call privileged instructions. Privileged instructions, and also it sends what they call common instructions. Okay, so privileged instructions are those instructions that are used to manipulate and manage key system resources. I repeat, to manage key system resources. And these instructions can be executed by programs of highest privilege level, and that is programs like the operating system that run at ring 0. Whereas common instructions here, they can be executed by programs, programs of the common, privilege level, and usually that is ring 3, like applications. Like if they are common privileges, like, they are already given permission to access, they'll just send the instructions directly to the hardware resources. But if they're now privileged instructions that are going to change the state of something, then those instructions have to go through the operating system. I hope, I don't know if that makes sense, but just take it that way. So in a virtualized environment, now we have come to what they're calling a virtualized environment. There is another special type of instruction that is called sensitive instruction. Like you hear the word sensitive. Sensitive instructions. And the sensitive instructions is used for changing the operating system mode or the operating mode of a virtual machine or the state of a host machine. And the instruction is handled by a hypervisor. And after a privileged instruction that originally needs to be run in ring 0 in the guest operating system is deprived of that privilege. Remember, now we have a scenario here. We have our guest operating system, but this guy is unaware that is a guest operating system. And for him, he knows, as far as let's give an example, as far as I'm a priest, I am entitled to such privileges. But this priest is not aware that he's now enslaved and is actually growing up in another kingdom which is not his, and is serving under someone else. So for him, he keeps on giving his servants instructions that, I'm privileged, please bring me breakfast in bed, please do this for me. And he's unaware. So because guest operating systems are meant to operate at ring 0, then we have a challenge. For them, they keep on sending privileged instructions, and yet remember, these things are running on top of a hypervisor, and yet they're supposed to, be sending common instructions. So that's why we come up with what you're calling sensitive instructions. So the virtualization technology, firstly, was applied to IBM, and the IBM mainframes implemented CPU sharing first, which was kind of easy method because they used to use an option of trap and emulate. When the kernel sends, the instructions, the hypervisor from this operating system will trap this, and it will emulate, and it will make it think that it's actually the boss and it's running on its own hardware resources. So it will trap and emulate and then pass on the instructions to our hardware resources. So using the depriving and trap and emulation, which was also called classic virtualization method, the basic principles were that the guest operating system runs at a non-privileged level, this way making it deprived of its privileges that it's supposed to be calling the hardware resources directly. And then after that, then the virtual machine monitor runs at the highest privileged level, which is ring 0. Now this is controlling the resources, so it is trapping and emulating. So when trapping and emulation takes place, this means that if the guest operating system keeps on sending more instructions, then the hypervisor is going to be overwhelmed because every instruction is coming through, and this makes it a bit more overwhelming for the operating system to take full charge of what is taking place. So that is how it used to happen. So now let us look and try and understand what full virtualization is. Full virtualization.
Sandy, could you please repeat the common virtualization? Common privilege.
Come again?
Could you please repeat the common privilege?
The common privilege?
Common instruction.
Repeat that. I said the common instructions.
These are common instructions.
Yes, these are instructions that are executed by programs of the common privilege level. The applications that run at ring 3. Okay? There are those instructions that are not going to change the state of hardware resources or that are not part of the privileged instructions. So I was just explaining the background, but now we're going to look at full virtualization and try to understand what full virtualization is. So full virtualization, when it comes to full virtualization, previously, like what IMB used to do, it used the classical virtualization methods, and they're not suitable for commodity 86 CPU best CPUs, right? And the root cause is that because these CPUs have extra 19 sensitive instructions that are brought about by virtualization, which are also beyond the privileged instructions. But remember, the hypervisor is now just trapping and emulating the privileged instructions that are coming from it. But now we have the 19 sensitive cases which are beyond the privileged cases. So CPU virtualization problems can be solved after only these sensitive cases have been taken care of. So what happens is that when it comes to virtualization, we have the 19, in full virtualization, we have the 19 sensitive cases which are introduced by commodity 86 best CPUs, and they have these 19 sensitive cases which also are now being set by the guest operating system. So how is it going to be identified? How are they going to be emulated? How are they going to be trapped by the hypervisor? Because these 19 sensitive cases identified are different from the privileged cases. So that's why these guys decided to come up with a technique which is called full virtualization. And in this way, because all request sets by the virtual machines need to be need to be virtualized and need to be trapped and emulated. So full virtualization was first proposed and implemented by VMware, and it translates the binary code of virtual machine operating system without modifying the virtual machine operating system. Virtual machine have high portability and compatibility. But now remember, whatever instruction comes, this guy is going to convert it to binary. This is now going to take a lot of resources. It's going to take a lot of resources. Whatever instruction is coming, convert it to binary and then process. Convert to binary and then process. Convert to binary and then process. And convert to binary and then imagine if the guest operating system and they are 5 and they are 6 and they're sending so many requests, then the hypervisor will get to a point and it's going to be, disadvantaged. So that's why the engineers are like, okay, this was good now, but because now we need performance, we need to look at performance, they decided to come up with what we are calling para-virtualization. Zen developed the para-virtualization technique, and we're going to look at it. With para-virtualization vulnerability, we already understand with all these mainframe, commodity 86 best CPUs, which has the 19 sensitive cases, and the problem is coming from these sensitive cases. So how about now, if we can modify the guest operating system, okay? If we can modify the guest operating system to avoid this virtualization vulnerability, and then the problem can be solved. So what do? Get the guest operating system, modify it and make it aware that, boss, you are no longer a prince. You are a guest now. You are running on top of a hypervisor. Please take note of that. So therefore, do not send your sensitive cases here, because now you are no longer the main operating system, but you're now a guest operating system. So that way it can help us to easily get rid of those 19 sensitive cases. But you already realized the problem. We already know that operating systems, we have open source operating system and we have closed source operating system. What comes to your mind when you hear open? It is free. We have access to the source code. We can modify, well and good. But the operating system which are closed, like Macintosh, like Windows, okay, we cannot modify such operating system because because it is closed source. So if you want to have a virtualized, we cannot have a virtualized operating system in para-virtualization. That is any of that. So that is a problem. The host operating system can be modified for only open source systems such as Linux, okay? But non-open source systems like Windows do not support para-virtualization. They get you when you have modified their source code for the operating system and they get a chance to get hold of you, you will pay dearly. Okay, because for them, they are into the business to make money and their source code is not available to the market for free. And then apart from this, now that's when they decided to come up with a third type of virtualization, which we are calling hardware assisted virtualization. They're like, now, okay, we tried full virtualization, we still have issues with performance and overhead. With para virtualization, yes, we can modify the guest operating system and make it aware that it is running in a virtualized environment. Well and good. Please mute your microphone. Someone has a very irritating noise like Glanda Makazu. Please mute your microphone. Okay. So we're saying they're like, you know what? This one, we don't have performance overhead. And now with para virtualization, we can only do that for open source. Now what do we do? How about if we, when we are making our CPUs, when we are making our hardware, why don't we, enable it so that it can actually support, virtualization, even minus it supporting it at software level. So they decided to come up with hardware assisted virtualization, and this type is very common today, and most of the laptops, hardwares, and servers that are produced today are hardware assisted virtualization. So in full virtualization and para virtualization here, that physical hardware does not support virtualization identification by default. If the physical CPUs support virtualization and are aware and they are able to identify sensitive cases, then it would be a revolutionary change to CPU virtualization. And that's why CPUs of mainstream commodity x86 host support hardware virtualization. Like Intel technology has the Intel VTX technology CPUs, and AMD has what they call the AMD's vCPU, which supports hardware assisted virtualization. So these guys are aware. Tanaka, I'm going to put you in the waiting room. I can't keep telling you guys to mute. I tell you to mute you. I keep reminding you. I just put you in the waiting room. But that way we shall move the class a bit faster. Okay, so that's why they decided to come up with hardware assisted. That the hardware itself, the CPU is aware that when I'm receiving 19 sensitive cases, they're coming from a virtualized environment and I need to process them accordingly. So that is what we are calling hardware assisted virtualization. Now, we said we are looking at compute resources, and we have looked at, we have already looked at CPU. Now it has also looked at memory virtualization. So we have looked at how we can virtualize CPU. Memory virtualization is another important type of compute virtualization besides CPU virtualization. So why does CPU virtualization lead to memory virtualization? With CPU virtualizations, virtual machines running on top of hypervisor have replaced physical hosts to run applications, and multiple virtual machines can run on the same hosts. And a host usually has one or more memory modules, isn't it? So how can memory resources be allocated to multiple virtual machines properly? Memory virtualization was introduced to address that issue. One problem with memory virtualization is how to allocate memory address spaces. And generally, a physical host allocates memory address spaces as follows. One, we need to know in physical memory addressing, the physical address always starts at 0. It starts at address 0. Two, starting from 0, the physical address allocated is also always continuous. So it starts from 0 and it goes to 1, then it goes to 2, 3, 4 in a continuous manner. However, after virtualization is introduced, the following problem occurs. There's only one memory address space whose physical address is 0, okay? And it has been allocated. Therefore, it is impossible to ensure that memory address space of all virtual machines on the host start from the physical address 0. And on the other hand, allocating continuous physical address of virtual machines leads to low memory utilization and inflexibility. That's why memory virtualization was introduced to solve problems concerning memory sharing and dynamic allocation of memory addresses. Memory virtualization is a process of centrally managing the physical memory of a physical machine and aggregating this physical memory and aggregating it and also passing it on to our virtual memory. So it's going to put them and put it in a pool of available addresses for our virtual machines to use. And memory virtualization creates new layer of address spaces, and this new layer of address spaces can be used by virtual machines. And these virtual machines, after that, they are made to believe that they're actually running real physical address spaces when in fact their access requests are relied by the hypervisor or the virtual machine monitor, which stores the mapping between the guest machine address spaces and the physical address spaces. So as you can see, what this memory virtualization is going to do, it's going to create and it's going to aggregate the physical memory into a virtualized kind of memory pool. And it's going to map this with the real physical memory addresses. So this is what is going to happen. Let us say this is memory address 0. Remember, it starts from 0, it goes to 1, 2, 3, 4, 5, and then it will go to 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, blah, 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 blah. So virtual machine 1, what is going to happen with virtual machine 1? This aggregated pool of memory resources are going to be of this color, right? So when this guy is also updating his addresses, memory addresses, what is he going to use? The memory address, the first memory address for this guy will be 0. What will be the next memory address for virtual machine 1? The next memory address for virtual machine 1, as you can see, which is mapped on our physical memory, it will be 5. This will be his address table. And the next one will be 6, and it will be mapped to and aggregated to our physical resources. And the next one will be 13, isn't it? And the next one will be 17. And the next one, the next address will be 26. Okay, so let us also look at virtual machine 2. Virtual machine 2, what will be the first memory address?
Will be 2.
It will be 2. Thank you. The next one?
26. 4.
4. The next one?
10.
The next
10.
one?
14.
14.
And the next one?
15.
15.
And 16.
16.
How about virtual machine?
14.
How about virtual machine 3?
3.
3.
3, very good.
9.
9.
Very good.
11.
Very good.
12.
Very good.
19.
Very good.
28.
28. How about virtual machine 4?
Will be 1.
Will be 1.
7.
7.
8.
21.
21.
21.
23.
23.
23.
24.
Very good. So that is how
29.
So that is how memory virtualization is going to get these addresses, and that is how it's going to map the physical to an aggregated pool of our physical resources. So let us look. We have looked at CPU virtualization. We have looked at memory virtualization. Let us look at the third one, which is the input or output virtualization. So here, emulation, which they called full virtualization, it is a complete simulation of hardware, for example, the keyboard and the mouse, input devices. This could be even the hard disk, this could be the mouse, this could be, you know, pointing devices like the pen I'm using, and all other devices that are going to either input or output our resources in the system. There could be buses, there could be anything. So here, with full virtualization, there's a complete simulation of all the hardware, for example, our keyboard and mouse. And access to such hardware depends on the capture focus by the hosts and leads to poor performance in some cases. For example, now, how do I tell that I'm inside my virtual machine? It depends on the area of focus. If I click on the area of focus, now my mouse is inside here, my virtual machine. And then that's why some hypervisor or some virtualization product tell you to press Control Alt to release the mouse. Okay, so that you can use it in another virtualized, to use it in your host operating system or in another, you know, virtual machine. So it entirely depends on the capture of focus, and also sometimes it leads to poor performance. So there's also another way, which is para-virtualization. And here access to hardware drivers is transferred from the input or output front end to the back end drivers. This mode is usually only used on hard disks and network interface cards and delivers high performance. Okay. There's also input or hardware input through, which is also sometimes called the hardware assisted kind of virtualization. So hardware devices capable of input or output through, such as hard disks and network interface cards, are allocated to virtual machines. In Zen, they have told us that DOM 0 or domain 0 allocates hardware devices, but it does not take part of the access of the hardware. And hardware support is therefore required or is needed. So let us look at the difference between cloud computing and virtualization. We already talked about it, and we said that cloud computing and virtualization, cloud computing relies on virtualization. Virtualization helps us to virtualize our physical resources at infrastructure as a service layer, and we can create multiple virtual machines, which the cloud computing technology purely relies on for us to be able to access our resources. So we go ahead and look at the mainstream compute virtualization technologies. Don't worry, the resources and the material will be shared. If I'm a bit fast, don't worry, we shall get the opportunity to share the resources. So with the mainstream compute virtualization technologies, we have two types, or we have two categories. We can see we have open source, and we also have closed source. When we say open source, it means it is free of charge or even open. The source code is open for, you know, modification. And as you can see, we can have two of them. We have KVM, which runs on top of Linux. It runs inside the Linux kernel, and we have Zen, which runs directly on the hardware resources, isn't it? It runs directly on the hardware resources. So we have closed source. We have Hyper-V. It is for Microsoft, and Hyper-V runs inside Microsoft operating system. And we have VMware EXI, and VMware EXI runs directly on top of the hardware resources, like the VMware servers that come and offered by VMware. We also have Huawei Fusion Sphere, also, which also runs directly on top of hardware resources. So we can see that open source, we can have type 1 or type 2, because KVM here is type what? Which type is KVM?
Type 2.
Type 2, which are sometimes calling hosted. And we can see Zen runs on top directly of hardware resources, which is type what?
Type 1.
Which sometimes is called bare metal. Okay, which we sometimes call bare metal. So these two can be used in that direction. All right, so cloud computing is a business model that provides users with IT services anytime, anywhere, whereas virtualization is an important technical means for implementing cloud computing. Okay, we have two categories. Like I've said, we have open source and closed source, and they are used for classification. Open source technologies include like Zen and KVM, which I've talked to you, whereas closed source virtualization technology includes like Microsoft Hyper-V, VMware Sphere, Fusion Sphere, etc, etc. Okay, so in open source virtualization technologies, Zen is on a par with KVM. And KVM, we're going to look at KVM in full detail. Let me just grab this. We're going to look at KVM in full detail, but they're saying these guys work together. KVM is a full virtualization product, while Zen supports both para-virtualization and full virtualization. KVM, a module in Linux kernel, and it used to virtualize CPUs and memory. It is a process of the Linux operating system, and the input or output devices such as NICs or DICs need to be virtualized by a tool called QEMU. And we shall look at QEMU in the coming slides, so do not worry about that. All right, so we shall look at QEMU in the coming few slides. So we want to now move to the next slide of KVM and try to understand. Okay, I was talking about KVM and Zen. We said Zen runs directly on top of hardware resources, whereas KVM, it runs inside the Linux kernel and it's installed on top of there. And for it to be able to, for us to have input and output devices of either NIC or disks, we shall need to use QEMU, and then we can install and run our guest operating systems. So KVM, let us look at the introduction of KVM. Huawei virtualization product earlier than 6.3 version were developed basing on Zen. But later on, they decided, someone is making some noise that is irritating. But later on, later than 6.3, they decided to develop a kernel-based virtual machine, which we are calling KVM. It is a kernel-based virtual machine. KVM is type 2 full virtualization, like you guys have told me, and it's a Linux. It runs inside the Linux kernel module. A physical machine with Linux kernel module installed can function as a hypervisor, and which does not affect other applications running on the Linux operating system. And each virtual machine is one or more processes. So you can run the kill command to kill the processes. So you can see we have our physical hardware with the resources, CPU, memory, network interface card, and of course our storage. So we have, you have installed Linux kernel, and then we can go ahead and install the KVM module, which we can use now to create different virtual machine 1, virtual machine 2, and we use QEMU to emulate our input or output devices, okay? And then of course we have other spaces in Linux, like the user space and the kernel. So a KVM module is installed on a common Linux operating system, and it has 3 running modules or mods. We have the guest mode. I don't know if the next slide talks about it. Nope, it doesn't. We have the guest mode, and basically in the guest mode, virtual machines including CPUs, memory, and disks run in restricted CPU mode. And we also have the user mode. With the user mode here, the quick emulator, which we are calling QEMU, a quick emulator typically runs in this mode. And QEMU emulates the input, I repeat, QEMU emulates the input and output requests. And then lastly, we have the kernel mode. And the kernel mode, in this mode, the hardware can be operated. This is where the hardware is operated. Okay, so KVM system consists of 3 parts. We have the KVM module, this KVM module. We have KEMO. Let me just remove everything. We have the KVM module, we have KEMO, and then we have the management tools. And we're going to look at the management tools and libraries. We're going to look at them in the coming slides. Okay, so the KVM module and KEMO are core components of KVM, and they form a full virtualization product. So we go to the next slide and we try to look at this management tool for KVM. We said KVM is a core of KVM virtual machine, and this module initiates the CPU hardware and enables virtualization mode, and it runs the guest machines in virtual machine mode and supports the running of the virtual machine client. KVM is composed of quite a number of things, but as you can see, all these things put together, KEMO and KVM kernel module form a complete. This KEMO and the KVM module, they form a complete virtualization technology. They form a complete virtualization technology. Okay, so in KEMO originally was not part of KVM, and it is a universal open source virtualization emulator and uses pure software to implement virtualization. Okay, and actually KEMO is interacting with our hardware. It emulates. You send a request, it picks it and emulates. This means that all interactions with hardware need to pass through KEMO, and therefore the stimulating performance delivered by KEMO is slow. That's why KEMO is able to simulate CPU and memory virtualization or input requests. So in KVM only, KEMO is used to simulate input and output devices. And KVM developers reconstructed KEMO to create what we are calling KEMO KVM. And these two, we said, form a complete virtualization product. KEMO KVM runs in the kernel space and KEMO runs in the user space. When the guest operating system issues instructions, these instructions are then depicted and taken on by KEMO to go ahead and use them. So in addition to these two that we have talked about today, we also have KEMO, KVM, which provides quite a number of tools for modifying, deleting, and creating virtual machines. We also have LeapVat here, and LeapVat is the most widely used tool for API for managing KVM virtual machines. LeapVat here, as you can see, is an open source project, and it is a powerful management tool. It is able to manage these virtualization products such as KVM, Zen, VMware, and Hyper-V. LeapVat is an API developed using the C language, and an API using other languages such as Java, Python, either Perl can be used to call this LeapVat API application interface to manage virtualization product. That's why LeapVat is used for many applications, including command set, Vit manager. These guys you're seeing here, Vit viewer, Vit install, and others. KEMO, like I said, I will repeat and wind up with KEMO and say KEMO is an emulation software tool for implementing input or output virtualization. Okay, and it has a poor emulation performance when it comes to if you give it to manage everything. And that's why when you go to a Windows virtual machine, typically its network interface rate card, the system can only support up to 100 Mbps per second. It cannot meet the high rate implementation or requirements for some application, and that's why they decided to come up with a new technology to support LeapVat or to support KEMO, which is called Virtual VAT.io. So virtual can increase the network interface rate of a Windows virtual machine from 100 Mbps to at least up to 10 gigabits per second. That is what we are calling KEMO, and we're going to look at it in the next if you like to understand what we're talking about. We said LibVat, it is developed based on the C languages and other languages, other APIs using like Python, using Django, using Perl, can actually call this LibVat API and use it in other virtualization products. Okay, so we have our node here, we have our Linux host, we have LibVat, and it has a wide range of management tools like Vit Viewer, Vit Manager, and all these are used to manage our guest operating system like previously explained. So the default KVM input process when we have not introduced VAT.io or virtual, we are going to talk about VAT.io in the next slide, but this is the default process of actually emulating an input or output process on KVM. At first, here we have our disk. The disk device of virtual machine is going to initiate the request, the input request. And after initiating the input request, it's going to be sent here on input or output trap code or the capture program, which is in the KVM module is going to capture the input or output process requests, performs the corresponding processes, and then puts the processed requests into the shared page. So after processing those things, it will go and then post everything inside our shared page. So the KVM module now will go ahead and be notified or notifies KEMO that, you know what, I have a new request in the shared page. Please go and get it. This notification will come from here and we'll go to KEMO notifying it that there's a new request here in our shared page. Then after receiving the notification from the kernel module or the KVM module, then KEMO will go and obtain the detailed information about the input or output request from this shared page. And then it will, after obtaining it, KEMO will simulate the request and calls the back or the device driver to running in the kernel mode based on the request information to be performed in, to either perform the real input or output operation. And then the device driver operation is then performed by the physical hardware through its device driver. These are already 6 steps. Then after processing it, it will go ahead and KEMO will return the operation result to the shared page here. It will return the operating result to the shared page and then notifies the KVM module that, you know what, you sent me to do something for you and I have your response in the shared page. Please go and collect it. Now the input or trap emulation code will then read the return result from the shared page, and after reading the shared return result, it will go ahead and return the results operation to the device driver inside the virtual machine or the guest operating system. And that is the process, that is the procedure, how input and output processes are performed originally without introducing VAT.io. So let us look at the next slide when virtual is introduced. When we introduce VAT.io, it helps us to speed up the entire process. VAT.io is used in the following ways. One, we have a VAT.io front-end driver. This VAT.io front-end driver, when the virtual machine initiates a request to operate, to input or output request, then our input or output operation request is not captured initially by the trap code. Remember, initially in the previous slide, it had to be captured by the trap code, and then the KVM module used to notify KEMO about the changes. Here it is not captured, but instead, the request is sent directly to the buffering. Okay, we have here our buffering, and the request is sent directly to the buffering, which is between our front-end driver and our back-end virtual IO drivers. At the same time, as it is doing that, at the same time, it will also go ahead and notify KVM module, which notifies the back-end drivers that, you know what, there's something in the buffering, please do ahead. This is happening at the same time. So after doing that, Kemo will go ahead and obtain the details from the buffering and then about that request. And then after getting the request, you can see already on step 4, Kemo goes ahead and tells the backend driver to directly call the actual physical resources to perform the input or output operation. And then the operation is completed by the device driver. And after it is done, then now Kemo will return the details to the buffering, VRing, and it will put the details there. And at the same time, it will also notify the front-end driver that, you know what, your request has been performed. Please come and pick your details from there. The front-end driver will obtain the details directly from it. And from there, it will return the results to the application in our guest operating system, which initiated the operation. The advantages, as we can see here, it saves hardware resources because it's even faster and even the steps are fewer as compared to the steps without introducing VAT-IO. And it reduces the number of input or output request paths, which helps us to improve performance of virtualization devices. Okay, VAT-IO it has been helpful and it helps us to increase on the speed of our virtualization process. So introduction to compute virtualization. We say the Fusion Compute is a Huawei's product, and Fusion Compute Sphere virtualization suite is a leading virtualization solution today. And this solution significantly improves data center infrastructure by efficiently and providing the benefits for consumers or for customers. One, it helps us to improve infrastructure resource utilization by utilizing and pooling all those resources together. It also significantly helps us to accelerate service rollouts. Sustainability reduces our power consumption by using tools like distributed power management, and also provides rapid automatic fault tolerance recovery for surfaces, thus decreasing data center costs and also increasing the reliability of our systems. Fusion Sphere Virtualization Suite virtualizes hardware resources using virtualization software developed on or deployed on a physical server, so that one physical server can function as multiple virtual servers, just like any other hypervisor or the virtual machine monitor. And it consolidates existing virtual machines on light load servers to maximize resource utilization, and also releases more servers to carry new applications and solutions. So Fusion Compute here is the cloud operating system software in the Fusion Sphere virtualization suite and mandatory component. It virtualizes hardware resources and centrally manages virtual resources, services, and user resources. It also virtualizes compute, storage, and network resources using virtual computing, virtual storage, and virtual network technologies. It centrally schedules and manages virtual resources over unified interfaces. Fusion Compute provides high security systems and also reliable, and it also reduces point of failures, helping us to secure our enterprises and also promote green and clean energy data centers. So Fusion Compute consists of two parts. We have the CNA, shall be talking about it more often, which we are calling the computing node agent. Computing node agent. And we also have the VRM, which we are calling the virtual resource manager, which we are calling the virtual resource manager. So in addition to both this CNA, computing node agent, and VRM, the virtual resource manager, we also have a unified virtualization platform called the UVT, and it's a unified virtualization platform deployed by Huawei. It is a hypervisor like KVM or like Zen, And the Fusion Compute Hypervisor adopts the bare metal architecture and can run directly on servers to virtualize hardware resources. With the bare metal architecture, Fusion Compute delivers virtual machines at almost server level performance, reliability, and scalability. When we get to the labs, you actually get an opportunity to see how Fusion Compute works, like how we can be able to virtualize the different underlying hardware resources to create virtual machines using Huawei's virtualization solution and technology. The architecture of Fusion Sphere is similar to that of KVM, and VRM functions as the management tool for KVM. Administrators and common users can manage and use Fusion Compute on the graphical-based portal of VRM. So VRM is web-based. Please take note of that. Web-based, and it is graphical. Okay, VRM is web-based and it is graphical. VRM is based on Linux operating system, and therefore also many Linux commands can also be used after you log into your VRM. VRM provides functions like it helps us to manage our storages, our compute devices, dynamically scale resources in a cluster, blah, 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 etc, etc. I think, okay, etc. But as you can see, the Fusion architecture, we have our VRM, which is a web-based graphical portal. You can see, graphs, charts, and you can use it to manage our resources. We have our cluster. We say that cluster is a group of, different physical servers put together, what we're calling hosts. 1, 2, 3, 4, 5. And these hosts are putting resources together, or they are going to share resources. We are connecting to our data stores usually, and we have a virtual pool of resources. We have our storage that is put together. We have our memory that is put together, our CPU and memory. We have our resources, and all these are put in a virtual resources, and we can use this through using VRM to create virtual machines. These resources are managed by CNA, and we use VRM to be able to access CNA, which is virtualizing our underlying hardware resources. So Fusion Compute advantages, we have said that it helps us provide a unified management of virtual and physical resources. We can manage our physical resources using Fusion Sphere, virtualize them, and we're able to access all these resources, virtual resources, using VRM. We can also quickly create virtual machines and provision virtual machines through the VRM, and we can create or delete or modify virtual machines using that virtualization product. So we are seeing here CNA. We said CNA is similar to KVM and KEMU module in KVM, and CNA provides the virtualization function. It's just going to help us to virtualize the different underlying hardware resources to create a pool of virtual resources. It is deployed in a cluster to virtualize. If you know your microphone is unmuted, please mute yourself. It is deployed in a cluster to virtualize compute, storage, and network resources in the cluster into a resource pool for users to use. And we said already, and we said again, and I'll say it again, that CNA is based on Linux, and therefore you can use many Linux commands to be able to manipulate and modify your CNA. So these are some of the functions between CNA and VRM. CNA deployed in a cluster for virtualization. VRM helps us to manage what this guy has virtualized, the virtual resources, okay? Okay, so CNA provides functions like providing virtual computing functions, managing VPNs on compute nodes, and also manage compute and storage resources on compute nodes. Whereas VRM, the virtual resource manager, helps us to manage block storage resources in a cluster, manage network resources such as IP addresses, VLANs, assign IP addresses to virtual machines, etc. So it manages the lifecycle of virtual machines in a cluster and allocates and migrates virtual machines across compute nodes. It also dynamically schedules resources in a cluster and manages virtual resources and cluster in a unified manner. It provides a unified web UI portal, allowing operations and maintenance engineers to remotely access Fusion Compute System to monitor and manage resources, and also create and view resource reports. So this brings us to this quiz, which says that in compute virtualization, which of the following allocates CPU and memory resources to virtual machines?
Hypervisor.
It's the host OS.
Host OS.
Hypervisor.
Host OS.
Guest OS.
Guest OS. I think it's the hypervisor. I think it's C. I'm not sure, but I think it's C.
It's the hypervisor.
Hypervisor. C.
In virtualization, in compute virtualization, I'll read the question again. Which of the following, let me turn on the messages. Remember I had blocked you guys from chatting. Okay.
The hypervisor.
The hypervisor.
Yeah, it's a hypervisor.
So in compute virtualization, which
It's the hypervisor.
all the following allocate CPU and memory resources
It's
to
a
virtual
host.
machine? Which
Guest
of the
OS.
following allocates
Guest OS.
CPU and memory resources to a virtual machine? I remember when I was illustrating something here.
It's the hypervisor.
Let me just come here. I remember when I was allocating something here, when I was creating this machine which has been created. I remember I went into the details. I even don't remember the password. Let me just shut it down. Let me shut down this machine. Just a moment, shut down. Yes, I have shut down my machine. I remember, what has happened to you? It has disappeared. Let me just open another one. Another one. Okay, I will stop the recording. Read the question again.
So
Are you
most
all
probably
seeing,
the
are you
answer
seeing
will
my
be host
screen?
OS.
Are you seeing my screen?
Yes, we are seeing it.
I created this virtual machine.
Hypervisor.
I created this virtual machine here and I named it Ubuntu, isn't it?
Yes.
I can even go ahead and create more virtual machines, isn't it?
Yes.
And
Yes,
I can get this virtual machine, right? And I can choose, you know what?
Yes.
I want to change its memory. I had initially allocated 4 GB RAM.
No, it's host OS. Host OS.
But now I feel like I need to give it more. I need to give it more memory.
Host
Or I
OS.
need to give it less memory.
Already said.
It's host OS.
I need to maybe, I had assigned it 2 cores. Now I need to assign it more processors.
Anyway, let him finish. Explain.
I need now to create more space. I had initially assigned it. Let me maybe go ahead and expand on the capacity and give it more resources. Or maybe the network interface card. This one was NATed. Let me add another network interface card. And it's going to be a network adapter. I go ahead and add it. Then on this network adapter, I want it to not use NATed. I want it to use, a private, and I want to give it a lane network segment. I go ahead and add IP addresses. You told me very well, what is this tool that I'm using to add resources and remove resources? You told me it's even an example and a type. Which type of hypervisor is this?
VM.
It is type what?
VMware.
Yes, it's VMware. But it's
VMware.
Hosted.
It is hosted.
VMware is hosted on top of.
Yes. So let me ask again before you answer. Let me ask again. When I am increasing the memory here, which tool am I using? Have I gone to my host operating system, or I'm using the hypervisor to actually either increase the memory? This is the memory of my machine. I can give it 5, I can give it 2, I can give it 2 GB. I can give it whatever memory I want, and I press on OK, and you see my virtual machine here will have 2.5 GB of memory.
I'm using the hypervisor.
Once again, once again.
Okay. I think it's a trick one. There we are working in the guest OS. That's why you're working in.
I'm not working against OS, even the machine is powered off. What are you saying? The machine state is even powered off. How do you say I'm working in against OS?
A virtual machine monitor.
Using the hypervisor.
Yes, it is the hypervisor I am using. I am using the hypervisor to manage my virtual machines, to either increase the memory, to either do whatever I want to do. I can even delete it and I can free these resources. I am using this hypervisor here.
Oh,
does that make sense?
Yes.
So I am using the hypervisor. So it is the hypervisor which is going to allocate CPU and memory resources to the virtual machines. I'm using that one to allocate those resources, isn't it?
Can you start recording, sir?
Can I what? The video is recording already. So it is the hypervisor. But remember, we said the hypervisor has another name. So this question in this case would be multi-choice. Pay attention to detail. Yeah. We said the hypervisor has another name. Which name?
VMM.
Virtual machine monitor.
Yes. So okay, Alex got it right in the chat. So even when you're answering, don't be too excited, but pay attention to detail, right? And this would be the correct answer. If you only selected one and you left out the virtual machine monitor, your answer entirely would be wrong. Okay, so let us now look at this. All open source virtualization technology are type 1 virtualization, while all closed source ones are type 2 virtualization. True or false? You give your answer and you give the reason why.
False. Maybe the answer will be true.
I repeat again. All open source virtualization.
Mr. Sandy, can you do a poll for that one? Can you do a poll? Can you launch a poll?
You want me to do a poll? Okay, just give me a few. Give me a few.
All open source virtualization technologies are type 1, while closed source are type 2. No, type 1 KVM is a type 2 in this.
Just give me a few. I'll be with you. On your screen.
The answer is false.
Someone requested for a poll.
The answer is false. The reason is that you told us that KVM is a Linux.
It's a ring.
And
you're signing to the bank.
Can you wait for a poll, please?
Sorry.
Oh, I don't say.
Yeah, sir. The poll you're sign to the bank.
No.
Bank.
Okay, all right, I'm done sharing now. Sharing now. You should be able to see it now.
Yeah, we can see.
Now we can see it. It's okay.
Yes, you have about a minute to complete it. So far, 100 people responded.
Kamel, I cannot get it.
You cannot get it, just check on your Zoom. It should be there.
I mean,
With two people walking side by side and another.
True.
Okay, I will end the poll now and share the results. This is how people have performed. What you're seeing on your screen. About 93% said the answer is false, and about 7%, 10 people said the answer is true. Now, let me stop sharing the results. For those who are saying it's true, can you help us tell us why you think your answer is true? Anyone?
Yeah. This is Jimmy.
Yes, Jimmy. Go ahead.
Yeah, the type 1 is only on a bare metal, and type 2 we can run on other operating system.
And type 2 you can run on other operating systems. Okay, that is true. That is true, but did you read the question very well?
Open source.
Okay, those who are saying it is false, could anyone just tell us why you think your answer?
Yeah, thank you, Mr. Samuel. You're speaking to Prosper. I think from what you just told us, you mentioned the fact that KVM is an open source and it runs on top of Linux. So that makes it type 2. And you also talked about the other open source, which is, what is it? I'm forgetting the other one from Huawei. Zen. Yeah, yes, Zen. And Zen is also an open source, though it is bare metal. So I think that's why it's false. Thank you.
All right, that is very correct. I will just take you back to this slide just briefly. Where was that slide? Okay. Where was it? I think I'm lost. It was here. Remember this slide very well? We said we have some virtualization tools which are open source, and we have some which are closed source. We said open source, they are what? Usually free, isn't it? And you can also sometimes modify the source code. Some of the operating system in open source, we have Linux, we have Android, etc. We have closed source tool applications. These ones you pay to access them. If you want to get Windows, Microsoft Windows, you pay, isn't it? You pay for the license to acquire it. And you cannot even access its source code to modify the content of the operating system, isn't it? Yes. And here the same applies, the same analogy applies to our virtualization tools. We have those which are open source, and we have those which are closed source. And we can see here KVM. We already agree because it runs on top of Linux. It is type what? Type 2, because it runs on top of Linux, right? And we have Zen. We said Zen is installed directly on top of the hardware. It directly calls the hardware, which makes it type what? 1. You remember me drawing this and illustrating this? Yes. Already, Zen is in open source, but it is type 1. And KVM is open source, but it is type 2. We come here to closed source. As you can see, Hyper-V runs inside Microsoft Windows, isn't it? Yes. Microsoft Windows. That makes it with type?
Type 2.
Type 2.
Type 2. Type 2 it is.
Because it runs inside of Microsoft.
Yes.
VMware EXI is a tool. It actually runs on top. It doesn't even need Linux or Windows. It comes directly installed on the VMware servers, which makes it type what?
Type
1.
Type 1. Also, this guy, Fusion Sphere, is installed directly, which makes it type 1.
Type 1.
Okay. So we can see already that we have some type 1, which are open source. We have some type 2, which are open source. We have some closed, which are type 2. We have some closed, which are type 1. We also have other open source virtualization tools like VirtualBox. VirtualBox is open source, isn't it? Download it and install it for free.
Yes.
But it is type 2, isn't it? Whereas VMware, they give you a free trial, but most of their products, you buy them. But it is also installed either on top of Mac OS or Linux or Windows, which is type 2. VMware Workstation, which is type 2. So that takes us back to this question again, and we'll read it one more time. And we say all open source virtualization technologies are type 1. That entire statement is already wrong. While all closed source ones are type 2. Also, that statement in itself is already wrong. So that means that our answer is false. Perfect. So this chapter has summarized the basic knowledge about compute virtualization, includes CPU, memory, and input or output virtualization. It has introduced us to open source virtualization technology by using KVM as an example, and also to commercial virtualization products by using Fusion's compute as an example. So recommendations, you can go and visit the e-learning platform, read some of these documents, and I'm going to be also sharing some of the material on group tonight. And having said that, I want to thank you for being part of this class. But before you leave the class, let me first stop.